Okay, now we are going to see climate plane. Now we are going to bring in the idea of connected particles. We covered connected particles, but we couldn't handle friction because we had not covered it yet. Now, the planes we are studying in that case, we are smooth, so it never felt anything like friction. So now we are having these ones when they are rough. So that's not the question direct. A block of mass 2 kg resting on a rough plane inclined at 30 degrees to the horizontal. So this plane is inclined at 30 degrees to the horizontal. We have a block. It's going to be a block of mass 2 kilograms. Okay. Is connected to a block of mass 3 kilograms hanging freely by a lightning extendable string passing over a pulley at the edge of the slope. So this one is connected to a block of mass 3 kilograms by a string passing over a pulley at the edge of the slope. Now this means that the light inextensible string means the weight of the string is negligible, and then inextensible acceleration is the same in these two. The acceleration that is going to be the same in that string. So that string cannot be stretched. Okay, when a system is released from rest, a 3 kilogram mass travels a distance of 0.5 meters before it attains a speed of 2.5 meters per second. That is the acceleration of the masses. Okay. Okay, so now we are telling us that when it's released, no acceleration now is going to be, because this one is going to be the one pulling. So we are going to have our acceleration in that direction. That's our acceleration, which will come also inside in that direction. Now from there, we are going to have the tension in the string. Okay. So this string is going to be having tension in it. And it's going to be the same because the string is the same. Of course, because this one is having mass, you are going to get weight by multiplying 3 times the gravity. All this one is also going to have we get the mass times B. Of course, it will be having a reaction there. So when you get that, okay, now let us resolve this weight here. You can now resolve it. This is 2d cos 30 degrees. This is 30 degrees. Then this is going to be 2d sine 30 degrees. Of course, because this plane is rough, we expect friction. Because acceleration in that order, friction is going to be opposite 8. So this friction is going to be opposing 8. Because the moment the body is in the motion, it means that we have already reached the maximum friction. So that's going to be our friction there. Okay, so basically that's what we had to do there. So part A, acceleration of the particles. So in my part A, first of all, the body was released from rest, meaning its initial velocity was 0. And then it reached a speed of 2.25 meters per second. What was the distance? The distance S was 0.75 meters. That's when it reached, after coming this, reached the speed. So there was one acceleration for this at this distance. So from there, so you have S, means that the basic equation, the third equation, it says U squared equal to U squared plus 2AS. If the body returns, this one now becomes negative. But now it's not returning. Because you see, the speed there you have 2.25 squared equal to 0 because the body was from rest, plus 2a, then our distance 0.75. And from there, our a is going to be, from there just press your calculator. Yeah. My expression here is 3.375 meters per second squared, and that's going to be the acceleration of the masses. So that direction there. Coefficient of the friction between the 2 kilogram mass and the plane. Okay, so there we come to our part B. They want this Remember our F, first of all, our F is equal to mu R. That is very clear. Okay, so meaning we need R before we get the F. So if I resolve along to the plane, I mean perpendicular to the plane in that order, start here, we don't have, if I resolve it along the plane like this, we don't have acceleration, I mean perpendicular to the plane, we don't have any motion. So meaning, from there our Fr equal to mass times acceleration, but A is equal to 0 for forces perpendicular to the plane. And if once we know this, it means that now we can, it means that these forces are balanced. So this is equaling to that force there. So it implies that now our R minus this one, the resultant force is this minus this, because they're the ones which are perpendicular to the plane, 2b, then cos 30 degrees will be equal to the mass, which is 2 times 0. So from there, so our R will be 2 into 9.8 into 3 over 2. So our R, from there, I think you see we can calculate our R, which you can, I don't know what you want. We can leave it to 4 decimal places. Here I get 16.9741 newtons. Or from here, consider we have 9.8 root 3 newtons. I'll give it 4 decimal places. Now, we now resolve forces that are acting in the direction of the acceleration, so along the plane. So, along the plane, in the direction of acceleration, so where acceleration goes is what we are studying also. So this acceleration, first of all, of the 2 kilogram mass. So now, what is pushing it in that direction first is going to be, it's going to be this T here, in that direction. So we have T. We know that what we are using is Fr equal to Ma. So my resultant force is going to be T, this which is pushing it up, then minus this force which is opposing, 2G, sine 30, then minus also our friction, this one, because it's accelerating, we are going to be having the mass, which is 2, then times the acceleration, which is 3.375. And so from there, you can clearly see that this one is going to be T minus 2 into 9.8 into a half minus F equal to 2. From there, you see 2 times, we get 6.75. If we make F the subject, so our F will be equal to 2. This is going to cancel, so we have this minus this. So this, we have T, then minus 9.5, then this one. So minus, we have 16.55, and I call this equation 1. So that our problem is coming in for this T. Now let us resolve also our acceleration in this order there on a 3 kilogram mass. So it's what is pushing it down. You know that our Fr is going to be equal to mass times acceleration. So our resultant force is going to be now 3P minus now the T equal to the mass, which is 3, and the acceleration, which is 3.375. And from there, you can say our T is going to be, when you take this side and bring this side, it's going to be 3 into 9.8 minus 3 into 3.375. So from there, our T is going to be So this one is 19.275 newtons. So we have our torque. So if we have this T, you can come and substitute here and we get our F. So put T in equation 1. So from here you have our F equaling to 19.275 minus 16.55. So our friction force is going to be 2.725 newtons. But remember, we want to get the coefficient of friction. So our mu R will be equaling to 2.725. Now we have our R. Our R here is 16.9741 equaling to 2.725. And from there, our mu, when you divide, you get 0.1605. That is going to be our coefficient of friction. So that was part B. Then we come to part C. Our part C, they want us to get the angle of friction. You know that from the tan of the angle of friction is equal to mu. So we have this. So this is equal to 0.1605. So meaning our lambda is going to be tan inverse of 0.1605. And so our lambda becomes 1.12 degrees. So give it to decimal places. 2 decimal places. And so the question is that. So that's how we handle that. Numbers, they are very easy. Once you have these ones, you remember always. Remember it's a string, expect tension in the string. Then dissolving is a very required thing for now. And then that's how we handle the question. So that's it, members. I wish you well.